Okay, great. So for the last talk of this session, we have U-turn, forward-driven backwards analysis for incorrectness by Roberto Bruni. So go for it.
This talk was supposed to be the last one today, so I had to anticipate a little bit. And I think that by looking at the previous talk, I could skip half of it, because we have seen most of it already. This is a workshop on static analysis. We have been speaking about correctness and incorrectness, proving the absence of bugs, or trying to prove their existence, right? Oops, too much. And a duality that will come be useful later on, observed by Peter, was that for correctness reasoning, you get to forget information as you go along a path. Is it working? Yeah. But you must remember all the paths as you do the computation. Instead, for incorrectness, typically, you remember information as you go along a path. You will find it in the post, but you can forget some of the paths. You can drop disjuncts. And our goal was to define a reasoning framework for incorrectness that aims to expose reachable bugs and also their origins, their source of errors. So for collecting semantics, we have seen it already. We can account for non-deterministic behaviors. Let me try to move here. Yeah. And so in general, given a source state, we can reach many target states, or we can also diverge. And the collecting semantics is seen as a function from the source states to the set of possible outcomes, which can then be extended by additive lifting to the power set of states, right? And we have seen already how our correctness and our incorrectness can be expressed through the collecting semantics as in terms of an over-approximation of the outputs or an under-approximation of the outputs, right? For this talk, I'm going to use another semantics, which is just the opposite of this relation. That is also known as the weakest possible prey by OR. It is different from the weakest liberal prey and the weakest prey that we've seen before. Essentially, for a given output, for a given target state, it tells us what are the possible source state leading to it. And using the weakest possible predicate transformer, we can express the necessary precondition logic as an over-approximation of the backward semantics. And Lisbon triples, sorry, I have to redo everything. Yeah, there is some delay. When I press the button, I have to wait a few seconds, so let me do it straight here. Yeah, there is maybe some interference. So this is known as Lisbon triples, it is known as BUA, and it is also known as sufficient incorrectness. I will stick to this name because I'm going to reuse the inference rules from this presentation. Let me use this. So you see the 4 logics I'm speaking about can be described by this taxonomy. And we will focus just on the incorrectness analysis side, so the bottom part of the diagram. And the aim of the 2 logics is slightly different. Incorrectness logic and their derivatives are aimed to expose reachable bugs. That's what they have been designed to. While sufficient incorrectness logic or backward under-approximation semantics aims to expose sources of bugs. So source states leading to some error in the end. I already classified this logic as a forward logic, and this is also observable at the level of the inference rules of the logic. I will go briefly through some of them. For the sequential composition, this is the classical one. For non-deterministic composition, from the same source states, you can reach Q1 by executing C1, and you can reach C2 by you can reach Q2 by executing C2. Then, by the non-deterministic composition of C1 and C2, with the same input, you can reach both Q1 and Q2. Right? And for the assignment, we can only use the Floyd axiom for assignment. The OR axiom would not be valid for incorrectness. And this one, as well as this one, makes it evident why it is a forward logic, because the rules are applicable to any precondition when you try to infer the postcondition. Okay? Let me also point out that for incorrectness, you can always have the false postcondition that will give you a valid triple for any command and for any precondition. And by the combination of this fact and this rule, we can drop some disjunct in the inference. For example, we can forget about the outcome of C2. Okay? And so in the tool developed from incorrectness, you may design different heuristics that tell you which path to drops at which point. For the sufficient incorrectness logic, the aim is to expose the sources of bugs. So it works backward. You imagine you have the postcondition and you want to infer some precondition that explain why the bugs are produced. For sequential composition, you have the same rule as the previous one, meaning that you can use it in both directions, in a sense. For the disjunction, for the non-deterministic choice, you may have different ways of producing the same output, and you collect them. And for the assignment, instead of using the Floyd axiom, you can use the OR one that is applicable to any postcondition. But in this case, also the Floyd axiom would be valid. And dually, now we can have false as a valid precondition for any command and any post. And the dropping of disjunct happens by moving backward. So we may decide which source to track when we have many variables. Okay, so let me come to the core of the contribution. We aim to combine incorrectness reasoning with sufficient incorrectness logic. And you see there is a semicolon here because we do this in this order. We compose them in this order. So the idea is to first prove that some bugs are reachable, starting from some precondition. And incorrectness logic will provide us with a guarantee that there are no false alarms this time. And then, taking into account this information, we exploit the sufficient incorrectness logic to trace back the precondition leading to those bugs, okay? Which in general will be a subset of the original preconditions. And the key idea is that in doing the backward reasoning, we will re-exploit the forward reasoning, the proof that those bugs are reachable. And so once the name of the presentation, we move forward with incorrectness logic, we find some bug, we turn back, and we try to detect the sources of those bugs. And so this is the overall idea from the technical point of view. Imagine that you have given a proof of incorrectness logic that this triple holds, and you have the whole derivation tree of it, where Q is some bug. Our judgment, building on this proof, will try to infer a precondition P prime that would be a subset of P, such that any state here can lead to some bug in Q. And this will be done inductively on the command C, of course, but also on the proof of incorrectness. So the inference rules are like this. So we have here, imagine a proof of incorrectness for a composition of two commands. And inductively, we look for the bugs that are reachable from the execution of C2, starting from some R1 that is a subset of R. Okay? Here we could start with Q. In general, the rule works with any subset of Q. We can focus on some bugs. We don't necessarily need to account for all of them. Once we detect R prime, we can reuse R prime will be a subset of R, and therefore we can re-exploit the previous proof of incorrectness for C1 to deduce P prime. This will allow us to conclude that starting from any state in P prime, by executing C1 and then C2, we can reach some of the bug in Q prime. Here is another example about the dropping of disjuncts. Maybe we have a proof of incorrectness that only cares about one of the branches. And so in order to derive the source of the errors, we will only focus on that branch. And we forget about C2. So the incorrectness proof that we made forward will be exploited when we are reasoning backward to decide which path to drop. Okay. And then for the assignment, just as another example, maybe we have some postcondition for the assignment obtained by the Floyd axiom. We can focus on some unwanted states of this postcondition that are errors. And then we apply the OR axiom to filter out those states of P that can produce those unwanted states. To conclude, here is just a simple faulty programs. It's a toy example and a doc one. So imagine that we init some array with length L, then we change the value of L, and then we compute again the length of the array. But unfortunately, the init function is wrong because for some values of L, for example, when it is 2, the initialization procedure forgets to insert the null value. Okay? And therefore, when we will try to compute the length, we will get into some error, right? We will try to access a part of the heap that has not been allocated. So using incorrectness logic, we may infer, starting from any precondition with no assumption on the initial state, for any state, that some error can be reached. Okay? And we get maybe a postcondition that is not immediate to understand. But then exploiting the proof of incorrectness and our system, we can infer automatically the proof that the precondition leading to the error is when L is equal to 2. So any state where L is equal to 2 will lead to that error condition, which is much simpler as an information to provide to the programmer with. So to conclude, in this work, we try to combine two different logics of incorrectness, of under-approximation. And one is moving forward and the other working backward. We could also dualize the approach, so starting from a sufficient incorrectness logic proof, and then derive a corresponding incorrectness logic proof to show that some bugs are reachable, which one, out of a larger set. And so in the end, we can say that the whole, the combination of the two, is more than just the sum of its parts, because in doing the second analysis, we can re-exploit what we learned from the first one. As a future work, we would like to integrate this approach with abstract interpretation and possibly with B-adduction strategies. And this was the take-home message that I prepared for the end of the meeting, but I will present it to you now. So you see that sometimes when different approaches are proposed, one tries to fight to say mine is better than yours. We can redo everything that was done before. But in general, my message that, as also many other talks already shown, that by combining different approaches, we can gain some more information.
Okay, great. So again, we'll do one quick. Okay.
Everyone. The funny thing is that in abstract interpretation, when you do static analysis, we do forward, post, backward, pre. But when you go in the abstract, if you iterate forward, backward, you get result that you cannot do with one forward, backward.
Yeah.
Have you the same phenomenon in the logic?
I think so, yeah.
Okay, so you iterate and you write another paper.
Yeah. It's a good point.
Okay, great. So let's thank the speaker one more time.